Yes, good afternoon to all. We are discussing unit number 4, that is analysis and design of steel beams. Okay, and in our last two lectures, we have discussed the what are the basic terminologies used for uh, beams. Okay, there are various terminologies like joist, girder, spandrel beam, lintels, purlins. So these all are the elements. These are all words are synonymously used as a beams, but the purpose of using the location where the beam has been used, depending upon that location, these are the different names for the beams. Okay, and after that we have discussed the types of beams. Okay, so basically there are two types. Okay, that is one called as a restrained beam and unrestrained beam. Okay, so restrained beam is also called as a laterally supported beam, and unrestrained beam is called as a laterally unsupported beams. Okay, and this is the basic formula of our flexure formula. M by I is equal to sigma by y is equal to E by R. So if you rearrange this formula, it will becomes M is equal to sigma into Z. Okay, so Z sigma is the material property. That is the your beam is made up of which material. If it is made up of steel, then steel stress we have to use. If it is made up of concrete, then strength of concrete comes into pictures like that. Okay, so sigma is the material property and Z is the section property. Section, whatever sections we are using. For example, if you are using a rectangular section, so uh, section modulus of rectangular section I like a BD square by 6. Okay, but again now we are using the limit state method. There are two types of section modulus. One is elastic section modulus, one is plastic section modulus, ZE and ZP. So section modulus play a very important role in deciding the strength of the beam. Okay, means ultimately the strength of beam depends upon the section modulus. Okay, that is the geometrical properties. Okay, and after that we have discussed the stress distributions diagram and tension and compression flange forces creates equal and opposite forces, and they are create a couple, and that couple is ultimately we call it as a moment of resistance. Okay, and moment of resistance is always more than bending moments for the safe design. Okay, बेंडिंग मोमेंट पेक्षा मोमेंट ऑफ रेजिस्टन्स हा जास्त असला पाहिजे तरच आपला बीम सेफ होईल. अदरवाईज काय होईल, बीम फेल होईल तुमचा. म्हणजे काय होईल, बीमची कॅपॅसिटी कमी आहे आणि त्याच्यावरती येणारा लोड जास्त आहे. It means your bending moment is more than moment of resistance, so such thing should not be there. Okay, so after that we have discussed the what is meant by lateral torsional buckling. This is the one failure modes. Okay, this is the one type of failure modes normally occur in case of a laterally unsupported beam. जेव्हा बघा आपल्या beam for the beams normally in case of a buildings or bridges, for the buildings normal span may be starting from 3 meter, 4 meter, 5 meter, maybe 6 meter. Okay, in bridges span of beam will be more than 10 meter, 15 meter, 20 meter. Okay, depending upon the length of the beam. So in that case what happen, if we are not providing the lateral restraint, if we are not providing the lateral restraints at suitable intervals, then beam will be acting like a laterally unrestrained beams, and due to that insufficient lateral restraint, beam is going to be deflect in lateral directions. Okay, beam is going to be deflect in lateral directions. First, see, it is subjected to transverse load. So first there will be a in plane deflections, that is vertical deflections. When vertical deflection reaches to its maximum limits, the beam start deflecting in lateral direction, in horizontal directions, and there will be a rotation of the section takes place. Section is going to be rotated. Okay, and angle of twist, that phi comes into pictures. Okay, and when angle of twist rotation comes into pictures, beam starts experiencing the torsion. Okay, along with bending moment, shear force, torsions comes into pictures, and after that our beam is going to be fail, and that phenomena is called as a lateral torsional buckling. Lateral torsional buckling. Okay, and remember this lateral torsional buckling comes into pictures in case of a steel beam only. The reason why, what is the reason? If you observe this steel table, we are using I section for the beam, and there are two values of moment of inertia for I sections, Ixx and Iyy. So you will find that Ixx is 3 to 4 times minimum, 3 to 4 times more than Iyy. It means section is weak along yy axis, so it is going to be fail in that yy planes. Okay, that is one things. And in case of a steel beam, I sections and laterally unrestrained beam. Okay, steel beam, if we are using steel beam and if our beam is having proper lateral supports, proper lateral restraint, then this phenomena has been prevented. Okay, this phenomena has been prevented. This is one things. And after that, we have discussed the uh, terminologies, means IS code provisions. IS code provisions for the laterally supported and laterally unsupported beams. Before that, we have discussed that these three actions are very important for the beam. Which are the three actions? Shear force, bending moments, and deflections. Okay, so whatever beams we are going to design, that beam must be safe in shear, safe in bending moment, safe against bending moments, and safe against deflections. Okay, so these are the three criteria. After that, the detailed, uh, not procedures actually, detailed formulations of the IS codes of laterally restrained beams. Okay, we have discussed that MD is equal to beta B ZP Fy by gamma m naught. Beta B is takes care of the section property. Whatever sections we are going to use for the beam, we have to classify that sections. Okay, whether that section is plastic, compact, semi compact, or slender. Okay, don't bother about slender section we are not using. We are going up to semi compact sections, and we have to take reference of table number 2 of IS code for the classification of sections. Okay, and that beta B takes care of the section, whether plastic, compact, or semi compact. ZP, plastic section modulus. Okay, now see, it is a limit state theory. So simply up till now, for the section modulus you simply called as a Z. Okay, but now that Z means that was the elastic section modulus only. But now in you have studied plastic theory also, so now there will be a clear indications or clear uh, notations. Elastic section modulus is ZE, and plastic section modulus is ZP. So whatever values given in the steel table, they are the ZE, elastic section modulus. Okay, plastic section modulus either we have to determine, or for the I sections, that values are given on page number 138 of the IS code. Okay, or otherwise, if you know the value of shape factor is equal to, it is the ratio of, ZP divided by ZE, elastic section modulus. Okay, so for the I section, normally the values of shape factor is in the range of 1.12 to 1.14. This is the one general range for the I sections. Okay, your shape factor for I sections will not be less than this value and not be more than this value. Okay, you just refer. Okay, you just refer. So and uh, so this value will be constant, 1.12 or 1.14. ZE you are going to determine from the steel table. So just ZP is equal to shape factor into your elastic section modulus. Okay, this way you can determine plastic section modulus. Okay, or otherwise the detailed procedures I think already you have discussed in your structural analysis unit number 6. Okay, that equal area axis, Okay, so that was there. Then Fy is the yield stress. Fy is the yield stress of the materials, and gamma m naught, partial safety factor for the yielding. Partial safety factor for the yielding. Okay, this has been taken from table number 5. Okay, so this is about the for the design bending strength. Design bending strength. This formulation has been given in section number 8, page number 52 of the IS codes. See, this is section number 8, page number 52. This is page number 52. M less than MD, laterally supported beam. Actually, it is on page number 53. Okay, page number 53. MD is equal to beta B ZP Fy by gamma m naught. Okay, beta b is 1 for plastic and compact sections. After classifying the sections, if your section is either plastic or compact, then beta b value is 1. Okay, if your sections falls in the category of semi compact, in that case beta b is the ratio of zd by zp. Okay, then rest of the things we have discussed. So this is about the bending strength. This is about the bending strength. Similarly, we have to calculate shear design shear strength also. Okay, design shear strength. So how to calculate design shear strength? Yes, design shear stress vd. Okay, so v shall be less than vd, जसा m shall be less than md होता. Okay, less than or equal to, less than or equal to. So m is the bending moments, md is the design bending strength. Okay, v is the shear force and vd is the design shear force. Okay, design shear force म्हणजे जो section, whatever sections we are going to provide, the capacity of that section in shear. Okay, each section is having is their own capacity. And how to calculate vd now? Vd is equal to, for that we have to refer page number 59, clause 8.4. See, is code reading is very important. Page number 59, 58, 59. Yes, this is 8.4 shear. 8.4 is for shear. V less than vd, and vd is equal to vn by gamma m naught. Okay, nominal shear. Okay, nominal shear and plastic shear is one and the same things. So vn is equal to see, vd is equal to vn nominal shear divided by partial safety factor, and nominal shear is equal to av. Av means shear area. V stand for shear, huh? A for area. F by w. Why f by w suffix comes into picture? Yesterday I have explained the reason. For the I sections, there are two flanges and one wave. Okay, so whatever bending moment is going to be created in your section, uh, is developed in the sections, that bending moments has been carried by the flanges, and the shear force has been carried by the wave. Okay, this is the basic, and this has been analyzed from our knowledge of strength of material. So we are, when we are with the nominal shear, we have to take the shear area, and shear area means area of wave, and f by w means yield stress of the wave divided by root 3. This is the equations. Okay, now f by w and fy for the flange, since we are using the homogeneous sections, we are assuming that f by w is equal to fy, it is 250 mpa. Av, so there are different views on the shear area. Okay, so for the shear area, for I section or channel sections, major axis bending, our is major axis bending. Hot roll sections, if our section, whatever sections we are going to use, that they are the hot roll sections. Okay, so it is h into tw. For the welded section, it is d into tw. Okay, see, d means the clear depth of the wave, and h means overall depth of the section. See here, the meaning of each term has been given. See, A is the cross section area, B is the overall breadth of tubular sections, breadth of I section of the flanges. D is the clear depth of the wave between the flanges. Okay, means only depth of the wave. Okay, only depth of the wave. H is the overall depth of the sections. Means our, we are using the roll sections. We are using the hot roll section. So in our case, our H will be overall depth of the sections. If you are using ISMB 500, so we have to take this H as a 500. Okay, this H as a 500. Uh, okay, so this is about shear. Now, these formulations we have discussed: laterally unrestrained beam, all formulation MD is equal to beta B ZP into FBD. See, I am repeating each and everything from the previous lecture so that your tune will be there proper. Okay, so proper understanding. So without of that, within a short 10 or 15 minutes, there will be a revision of all the things whatever we have studied earlier. Okay, so beta B is common, ZP is common, only FBD is the change. Okay, laterally unrestrained beam मध्ये. Okay, and calculation of this FBD will be a very lengthy task. Will be very lengthy task. Okay, and FBD is called as a design bending compressive stress, calculated as below. Okay, FBD is equal to Zeta Lte Fy by gamma m naught. Zeta Lte is the bending stress reduction factor to account for lateral torsional buckling. हे बघा, lateral torsional buckling comes into laterally unrestrained beam, therefore this has been comes into picture. Lateral torsional buckling is not occur in case of a laterally supported beam or laterally restrained beam, therefore this Zeta Lte picture not comes into pictures. Okay, that's these are the difference. Okay, then this is Zeta Lt formulations, it is less than or equal to 1. Then phi Lt, alpha Lt, imperfection factor. Yesterday we have discussed what is imperfection, that nothing is perfect, so there will be a slight deviation in the cross sections. Okay, sizes, initial straightness, these are the causes of the imperfections. So for roll section it is 0.21 and welded section is 0.49, and this is lambda Lt, and after that this is FCRB big formula. Okay, so this is about the our basic formulations and basic procedures of laterally restrained beam, laterally unrestrained beams, what are the different formulations, how to calculate MD, that is design bending strength, how to calculate design shear strength, how to check for deflections. Okay, actual deflection we have to calculate. For example, if condition is given that simply supported beam subjected to a point load of 60 kilonewton acting at the center of the beam, then we have to calculate the actual deflection in the beams, and we have to check for the permissible deflections. Permissible deflection is given in table number 6. Okay, so these all these criteria, where whatever we have discussed basic things, these all things we have to say, we are going to cover by taking the examples. Okay, so first of all, now in today's class I am going to take the very basic and fundamental examples. Okay, if you understand this example properly, your design of beam is over. Okay, that's it. Because after that, what I did, I have so write down this step by step design. There are 7 to 8 steps are there, and step by step you have to proceed further, and your design will be complete. Okay, but these that are the mechanical procedures. Okay, you have to understand the basic what is happening. Okay, so uh, this is the very basic problems. Okay, so just try to understand this. Okay, now see, ISMB 400 used as a laterally supported beam of span 5 meter. Calculate the largest load the beam can carry. Calculate the largest load the beam can carry. See, beam section ISMB 400 is given. The support condition is it is laterally supported, laterally supported beam. Okay, span of the beam is given as 5 meter. We have to calculate the largest load the given the beam can carry. Okay, so to understand these problems, first of all, we must know that what are the different actions that beam is subjected to. Okay, so we know that when any beam is subjected to a transverse load, there will be a bending moments, there will be a shear force, and there will be a deflections. So we have to consider these three criteria. Okay, so first of all we are going to calculate the load from bending moment criteria. Load from bending moment criteria. So now how to calculate? See, step number one, load from bending moments criteria. Actually it is not a step number one. This we are going to follow three steps, for example, and we are going to calculate load from bending moment criteria. First case, case 2. Actually it is not step 1, it is case 1. Okay, it is case 1. Case 1, load from bending moment criteria. Case 2, load from shear force criteria. Case 3, load from deflection criteria. We will get three values of the load, and out of that three, which value will be the design largest load that we are going to discuss. Okay, so let the load on the beam size is W kilonewton per meter. Okay, ISMB 400. First of all, note down the all properties of ISMB 400 from the steel table. These are the properties I have noted down. Thickness of flange is 16 mm. Thickness of web is 8.9 meter. ZP. ZP is the plastic section modulus, that is 1176.18 centimeter cube. Okay, this value from steel table. Steel table, page number 130. Sorry, from IS code. ZP से प्लास्टिक सेक्शन मॉड्यूलसाठी आयएस कोड रेफर करायचा. हे बघा, पेज नंबर 138. आय विल ओपन अगेन सो दॅट यू विल गेट द थिंग्स. 138 ॲनेक्झर मध्ये दिलाय ते. 138 at last there will be an annexure. 127 133, 37 and 38. Yes. Then ISMB 400. Where is ISMB 400? This is ISMB 500. ISMB 400 is where? ISMB 400. Yes, this is the section. So its weight is, this is 61.5 kg per meter. Okay, this is area, width of flange, depth of the section, h. Width of the section, width of the flange is 140 mm, thickness of flange is 16 mm, thickness of wave is 8.9. These are the radius of gyration, RXX, RYY. The RXX is called as RZZ. Then this is moment of, section modulus. See, ZEZ, elastic, it is simply called as a section modulus, okay? And we call it as elastic section modulus. It is one and the same things, ZEZ. So it is 1020, and ZPZ 1176.18, and its shape factor is 1.1498. So these are the properties we have to pick up from the page number 138. Okay, so how much is ZPZ? Was 1176. 1176. See, this is here. Okay, so now M is equal to 1.5 factor load, where we have to convert working load into factor load. So 1.5 into W1 L square by 8. Okay, W1 L square by 8 means I am assuming that there will be a, this is W1 external load. Okay, there is a external load, as well as there will be a self weight of the structure. Okay, and self weight is also acting in the form of UDL. Okay, self weight कसा काढायचा? See here, running meter weight is given. How much? 61.5 kg per meter. As a unit बघा, see, kg per meter. This is nothing but the UDL of the beam. So 61.5 kg per meter. We have to convert this 61.5 kg per meter into kilonewton per meter. कसं करायचं? kg ला न्यूटन मध्ये करायचं आहे. 61.5 into 10. 9.81 it is there, but convert directly as a 10. Multiply 10. So 61.5 into 10 means 615. It is Newton per meter. Now 615 divided by 1000. Divided by 1000. So it is 0.615 kilonewton per meter. See here, 0.615 kilonewton per meter. This is the self weight of the beam. This is the self weight of the beam, and we are going to calculate this W1. This is the external UDL acting on the beam. Okay, so this is the external UDL and self weight, and it is acting in the form of UDL. So bending moment is WL square by 8. So there are two UDL. One is the, this is the external UDL, external load, and this is the self weight of the beam. Okay, for any structure or any element, there will be a self weight. Okay, म्हणजे फॉर एक्झाम्पल तुमचं स्वतःचं वेट आहे, तुम्हाला स्वतःचं वेट आहे ना, 50 kg, 60 kg, 70 kg. That is the self weight of your of you. Okay, so when we are similarly the self weight of beam is there. ISMB चा 400 चा जो सेक्शन आहे ना, त्याचं स्वतःचं वेट. ओके, अँड दॅट वेट इज इन दी लाईन लोड. It is acting in the form of a uniformly distributed load. So that is given in the steel table or IS code in kg per meter, that we have converted into kilonewton per meter, and that is again acting in the form of UDL. So WL square by 8, simply supported beam subjected to UDL over the entire span. Bending moment is WL square by 8. So just calculate, this is 1.5. It comes out with 3.113 W. It is 1.93. So make it is 4.7 into W1 plus 2.9. Okay, so this is the bending moment. This is the bending moments. Okay, now for the safe design, we have to equate this bending moment is equal to your moment of resistance or design bending strength So MD is equal to design bending strength का formula काय है? For laterally supported, MD is equal to beta B ZP Fy by gamma m naught. Okay, beta B is 1. Okay, let us not assume that section will become a compact section. Plastic section. ISMB 400 जो आहे ना, it will become a plastic sections. Okay, इथं मी क्लासिफाय नाही केलं आहे तो, you can classify later on. Okay, that is B by TF and H by TW. D by TW. So beta B is 1, ZP is 1176.18, Fy is 250 divided by 1.1. So it comes out to be 267.31 kilonewton meter. It is the design bending strength. Okay, so now equate bending moment is equal to moment of resistance. Okay, or design bending moments. Equate these two. So it is 4.7 W1 plus 2.9 is equal to 267.31. Therefore, W1 is equal to 56.25 kilonewton per meter. 56.25 kilonewton per meter. This is the first load we got from the bending moment criteria. This is the first load we got from bending moment criteria. Now second criteria is the load from the shear criteria. Shear means shear force. Okay, so first of all we have to calculate nominal shear. Vn is equal to Av into Fyw divided by root 3. Av is the shear area, and we have discussed Av is equal to H into Tw. H is the overall depth of the section as per the IS code. It is 400 because our section is ISMB 400. So overall depth is 400. Thickness of wave is 8.9. So area is 3560 mm square. Vn is equal to Av 3560 into Fyw yield stress 250 divided by root 3. It is 513.84 kilonewton, and Vd is equal to design shear force Vn divided by partial safety factor is equal to 513.84 divided by 1.1. Okay, it is 467.13 kilonewton. Okay, हा shear force आहे, so it is in kilonewton. हे bending moment होतं इथं, so it is kilonewton meter. Okay, unit, you are very much careful about the units. So now we got the design shear capacity of the sections. Now what is shear force in case of a beam subjected to UDL reaction? It is nothing but this is WL by 2 and this is WL by 2. Okay, जसं ते WL square by 8 होतं. Okay, bending moment will be WL square by 8. Okay, for this case. Similarly, for this case, shear force will be WL by 2. Okay, तुम्हाला सिम्पली रिएक्शन काढायचे आहे. दॅट्स वाय दी नॉलेज ऑफ शिअर फोर्स अँड बेंडिंग मोमेंट व्हेरी इम्पॉर्टंट. ओके, आय डोंट नो, कारण मला चेक पण करता येत नाही तुम्हाला येतं का नाही आणि तुम्ही लोक बोलत पण नाही आहे. So this is about the WL by 2 reactions. Okay, just recall your strength of material. Now shear force is equal to V is equal to 1.5 working load into factor load. W2, now I will call it as a W2. Means load from second criteria. Okay, actually W2 and W1 is same, not different, but just criteria has been changed. One for bending moment criteria, two for shear. Similarly, 3 comes for the deflections. Okay, so W2 into L, it is 5 divided by 2. Okay, WL by 2. Okay, so this is for the external UDL. Okay, now for self weight plus 0.612 into L divided by 2. Okay, so 3.75 W2 plus 2.31. Now similar way, as you equate MD is equal to M, similarly equate VD is equal to V. Design shear force is equal to actual shear force. Therefore VD is 467.13 is equal to 3.75 into W2 plus 2.31. Now therefore W2 is equal to 123.9 kilonewton per meter. This is the second load comes from the shear criteria. Second load comes from the shear force criteria. Okay, so we got two values of load. Now the third load, the third failure criteria for the design criteria for the beam is deflection criteria. So we have to calculate the actual deflection and permissible deflections, and we have to equate that actual deflection is equal to permissible deflections, and from that condition we will get the third load. Okay, so page number 31, table number 6. Page number 31, table number 6. Permissible deflection चा table आहे तो. Just wait, I will show you that table and how to use that table. Sorry, I scored सरळ कसा आहे हा. अच्छा, just wait, I will rotate it. Yes, page number, table number 6. Yes, this is table number 6, page number 31. See the title of the favorite deflection limit. These are the permissible deflection limit. Now there are some additional things comes into picture. So this table depends upon, see, type of building. Our building is industrial buildings. Deflection is vertical. Okay, see, there are vertical deflection, lateral deflection, but this is for the gantry girder. We want vertical deflections. Design load, live load. Okay, our is live load. Member, our is simply supported beam, so simple span is there, live load is there. And supporting system, it is a brittle cladding, for example. Okay, there is a elastic cladding and brittle cladding. These are the two terms you have to understand. Okay, see, not this table is given for the design of steel structure. Okay, normally steel structure are the industrial buildings. Okay, in case of a industrial building, supporting system is the that GI शीट्स और AC शीट्स. तुम्ही बघा, ट्रसच्या वरती ज्या वरती शीट्स असतात ना, दे आर कॉल्ड, दे आर GI शीट्स और galvanized iron or AC sheets. AC sheets nowadays are obsolete, no one are using. So if your supporting system is GI sheets, it means your that GI sheets comes under the category of elastic cladding. Elastic cladding. Okay, if you are doing check for that elastic cladding, if it, so your permissible deflection will be span by 240. स्पॅन म्हणजे आपल्या केसमध्ये किती आहे, स्पॅन 5 मीटर, सो 5000 divided by 240. But sometimes what happen, there are a composite structures are there. Composite structure म्हणजे काय, what is mean by composite structure? Means beams and columns are made up from steel section and slab is made up from RCC. Okay, and that buildings are called as a composite structure. For example, जे वर्ल्ड ट्रेड सेंटर पडलं होतं अमेरिकेमध्ये, they are the composite buildings. Okay, and composite buildings is having a very good performance because it is a combination of steel and RCC. It is a combination of steel and RCC. So what are the good points of steel structure and good points of RCC structure? Both have been incorporated, both have been taken care. So if your supporting system is a slab, RCC slab, and RCC slab is treated as a brittle cladding. Brittle cladding. Okay, so if your beam is supporting system is a RCC slab, your permissible deflection limit is spanned by 300. No, what is it? What is the philosophy behind this? Okay, not philosophy. Yeah, now what is the reason behind this? Okay, elastic cladding. GI sheets का असतं, it is a elastic in nature. It is deflect more. Okay, so that's why span by 240. This limit will be, permissible deflection will be more. But in case of RCC slab that is a brittle material. Okay, it is going to be deflect very less. So span by 300. 300 comes into denominator. It means permissible deflection will be very less because it is a brittle cladding. It is not going to be deflect more. Okay, so this is the reason behind these values, span by 240 and span by 300. Then this is for our beam case. Okay, these are, if your beam is cantilever, you have to use these values. Elastic cladding span by 120, brittle cladding span by 150. And cantilever beam is very sensitive. It is unstable. Okay, so त्याच्यामुळे ते बघा, permissible deflection will be more. Okay, permissible deflection will be more. Span by 150, बरोबर ना, deflection वाढेल ना span by 150 मध्ये. So, and for purlin and guts, this we are going to discuss when we are designing the purlins. Okay, so now our third criteria. Okay, just wait for 10 minutes. Page number 31, table 6. Type of it depends upon type of loading with respect to nature of supports that we have discussed. Now our beam is subjected to UDL. So formula of deflection for actual loading, 5 WL4 upon 384 EL. Okay, 5 W3, W1, W2, W3 and L4 divided by 384 EL. This is the formula for actual deflections. Okay, is equal to span by 240. Span by 240 केलं ना मी इथं. So I think I have considered it as an elastic cladding. Okay, these are the assumptions initial. Okay, span by 240 means the criteria of elastic cladding has been assumed. Okay, so now see here, one thing is that here I have multiplied 1.5 conversion of working load into factor load in case of a shear criteria. Similarly, in case of a bending criteria also multiplied by 1.5. But in case of a deflection, here 1.5 not comes into picture. Now why? The reason is that it is a it is a deflection check is the deflection criteria comes under the limit state of serviceability conditions. Okay, and serviceability means deflection is a day-to-day phenomena of our daily lives. Okay, so the partial safety factor for limit state of serviceability in deflections, it is always 1. Okay, it is always 1. So that's why here multiplied by 1.5 not comes into picture, means whatever deflections we are going to calculate, they are based on working load, not factor load. These the very important points you have to kept in mind. Okay, the reason is that because deflection is a day-to-day phenomena, there is no point to multiply the 1.5 for the deflections. Okay, so that's why that 1.5 comes not into picture over here for deflection criteria. You make a note liya tumhala, because after that you will forget why here 1.5 not comes into pictures. Okay, so it is span by 240. So now E is not given, so E, our beam is steel beam, so standard value we have to pick up from the steel, from the IS code given, in the IS code given. I is the moment of inertia, that is Ixx. From the steel table we have pick up. Now equate 5 W3 L4 5000 into 10 to the power 4 divided by 384. E is 2 into 10 to the power 5. I is this one. E is equal to span by 240. Span of our beam is 5000 divided by 240. So W3. W3 comes in. Only W3 is unknown. Now W3 is equal to 104.74. Now we have got W1. W1 बघा किती आहे? W1 आहे 56. W2 आहे 123 and W3 आहे 104. इथं लिहितो मी. जस्ट नाउ I have to conclude today's lecture. W1 is equal to 56. मी पॉइंट्स लिहित नाही, ठीक आहे. W2 is equal to how much? 123. Yes, 123. And first is load from bending moment criteria, second is load from shear force criteria, and third is load from deflection criteria 104. Now see, tell me the largest load the beam can carry. Anyone? आपल्याला विचारलं काय होतं, लार्जेस्ट लोड द बीम कॅन कॅरी. किती आहे लार्जेस्ट लोड? 3 व्हॅल्यू पडला, W1 W2 W3. येस, एनीवन? 56 123 104. एनीवन तुमच्या समोर आहे ना? कोणी पण सांगा मला, एक पण. चला लवकर कन्क्लूड करायचं आहे. येस, एनीवन? लोड सांगा मला, ते लार्जेस्ट लोड 3 पैकी लार्जेस्ट लोड कुठलं असेल? 56 असेल, 123 असेल का 104 असेल?
W2.
Yes.
W2.
W2. Yes. That's why I have to share. Our question is that the largest load the beam can carry. Now here see, we got load from bending moment criteria 56. Load from shear criteria is 123. W3 load from deflection criteria is 104. But now our beam is going to be fail when when W1, our beam is going to be fail at the minimum load when it is going to be subjected to 56. म्हणजे बेंडिंग मोमेंट क्रायटेरिया मध्ये कॅपॅसिटी किती आहे? 56. तुमचा when your load reaches to 57, your beam is going to fail in bending moment criteria. When your load reaches to 57, more than 56 पेक्षा जास्त लोड तुमच्या बीम वरती ऍक्ट झाला, it means your beam is not able, it is definitely, it is in shear it is 123, in deflection it is going to be carry 104. But what is happening about bending moments? When your beam is not able to carry the load from more than 56, because when load increases more than 56, it is going to be fail in bending moment criteria. So the largest load the beam can carry is 56. This is the point I have to emphasize. Are you getting or not? You imagine the things. टेन्शन मेंबर मध्ये काय केलं होतं आपण ना? TDG काढला, TDN काढला आणि TDB काढला, बरोबर? TDG काढला, TDB काढला आणि TDN काढला. Out of that, whichever was minimum, that was the design tension. Similarly here, whichever is minimum from the 3 criteria, that is the largest load the beam can carry. That is the largest load the beam can carry. This is the one basic fundamental example. If you understand this problem completely, you will your unit number 4 is completely over. I will declare. Just as a sake of our steps procedures, I will take one examples on design of laterally supported beam and one examples on design of laterally unsupported beams. Your unit number 4 is over. So this is the very important problems. You will never find this example in any of the books. In any of the books, this copy I have already uploaded on the Google Classroom, and I think we have completed the recordings of the today's sessions also. Okay, so are you gotten on na? Alan Lakshat, 50, why 56 is there? Because when it is reaches to more than 56, it is going to be fail in bending moments, though it is safe in shear. But we have to satisfy all three criteria together simultaneously. Okay, yeah, all three criteria have to satisfy together. Our beam must be safe in bending moment, must be safe in shear force, must be safe in deflections. नुसतं एकामध्ये सेफ असून चालत नाही. एकामध्ये सेफ आहे, दोन मध्ये सेफ आहे आणि एक मध्ये फेल होत आहे. इट मीन्स अल्टिमेटली अवर बीम इज गोइंग टू बी फेल. Okay, so this is the our design of the largest load the beam can carry.